Oops.
Okay, so good morning, everyone. So today is our second lecture, so Tuesday, second lecture with team. And as a kind of housekeeping announcement, so the lecture slides and the code in PDF format. So unfortunately, our MoCaO website doesn't accept MATLAB code. So it is on our website. And the YouTube channel, it was updated yesterday quite late. So if you had a chance to watch it in the morning, then yes, but probably not yesterday night. And we'll probably keep the same procedure for the rest of the week. So the documents will be uploaded on our MoCaO website, and the recording will appear eventually on YouTube. Okay.
Okay,
so yeah, we can start. Yep.
Okay,
Thank you.
Thanks, Nadia. All right, great. Welcome back, everybody. So, getting into the theory of the Arnoldi method today. So we introduced the concepts last time. So what did we talk about? So here's what we talked about. We've got this idea that we want to build a Krylov subspace. Okay, now why a Krylov subspace? Well, what could be more natural than a space built up by the span of B and AB and A squared B, given that what we have to start with is an A, and for the eigenvalue problem, we just invent a B. For the linear system problem, B will be part of the inputs as well. And so we derive this process called the Arnoldi process, which generates an orthonormal basis for that space. And it passes up the information to do so in a couple of matrices. Okay, so there's this V, which is the actual vectors that we want. And there's this sort of bookkeeping matrix H, which records all of the dot products and the norms that we used in orthogonalizing and then normalizing our vectors on the fly. Okay, so Nadia asked a great question last time about, what's this about doing it on the fly? So here we see, right, that inside our loop, we are multiplying the previous vector in the space, in our basis, by A, not the B. Okay, so we start out with a B, which we normalize, but every other step when we're building the next vector, we're multiplying the previous vector that we had. Okay, we're not actually going back and forming A times B and A squared times B and so on. And now the reason we do that is because we want the orthogonalization to happen at the first opportunity. Okay, we don't want to build the space all the way out to this, final vector A to the m minus 1 times B, because that's going to look just like A to the m minus 2 times B, or at least it's going to point in more or less the same direction. Okay, that was the reason that the PoW method worked in the first place. But I went away and I did it. Okay, so let's see this in action. Just how bad can it be if instead of doing the Arnoldi process, we just generate the basis as written and orthogonalize it once at the end. Okay, so to illustrate the breakdown in that, I'm going to use a much bigger matrix as an example. Okay, so this is a proper sparse matrix from a real application with a certain structure and so on. And so we're going to start with a random vector, as we always do. And let's take it out to m equals 80. Okay, so the dimension of this matrix is, into the thousands, so 80 is not so big. All right, so here's the naive choice of basis, right? Here we literally are just multiplying A times B and A squared times B, all right? There's no orthogonalization going on here. We will scale it so that it doesn't blow up, okay? But there's nothing like a Gram-Schmidt going on in this process, right? This is the vectors we would have formed if we did the PoW method, okay? So it's just A times the previous vector that's been normalized, nothing more than that. Okay, now here's our Arnoldi version, where we actually do orthogonalize every time, right? We multiply the vector that we had in the basis last time around, and then we subtract away the projections and so on. Okay, well, you can look at the difference in the conditioning of these two matrices and see that the difference couldn't be starker, all right? So our VM, which is just the first m columns of V, is perfectly conditioned, literally the perfect number you can get, which is 1. Of course, all right? The matrix is a built up of columns that are orthonormal. K is not at all that, all right? It's getting more and more like a matrix where the columns look like linear dependence, okay, especially the last columns. Okay, but, you know, what if we just orthonormalize this K, right, at the end of it all, using Gram-Schmidt or, you know, some more stable method? We'll just use the QR function in MATLAB. And what are you talking about, Tim? Look at that. Conditioning is perfect, right? Condition number of Q is 1 now. So problem solved, surely. No, not problem solved. Where's that condition number gone? Well, it's just migrated into R. Okay, so yes, K was badly conditioned. Q isn't anymore, but R is. Aha, you say, but who says we have to use R? What if we formulate our calculation from here to never actually use this R? We just use the Q, right? Because we remember that the projection of A onto its own Krylov subspace is, well, yesterday it was V transpose AV, this time, well, it's Q transpose AQ, and Q is fine. Okay, so here's H2. Certainly looks up a Hessenberg. Okay, modulo some, obviously small round-offs there, but there's an H. What's wrong with that H? Okay, maybe it's fine. In fact, here's the H that we got from the Arnoldi method. I'm not even sure I can see the difference. Okay, except for choices in sign, and that's just related to how MATLAB does the orthogonalization inside the QR function. But that's consistent, right? So the columns of the Q go with this H, and the columns of the V go with this H. Looks about the same. So let's just try a couple of eigenvalues. Here's the largest two of A. Okay, so these are our targets, if you like. And this is what we know and love from yesterday. Here's Arnoldi. Okay, so we take a couple of eigenvalues of H, and yep, pretty decent match. Okay, we seem to be getting convergence. I mean, M is 80 here, so, that's kind of reasonable. And then this naive approach using H2 kind of also looks okay. All right, so when I did this last night, I'm thinking, I know this is going to go wrong at some point, and I was surprised it lasted this far. But at least at this point, things might have been okay, but we're not done. Okay, we've got to actually calculate Ritz vectors. Okay, so the Ritz vectors come from taking these eigenvectors on the small scale and mapping them back up to the large scale via the V. And this is the full residual I'm computing here. So how good does this Ritz pair do as an eigenpair, right? Is A times U equal to theta times U? Yep, pretty much. Okay, so both of those are well converged. Okay, well, we'll be perfectly fair. We'll do the same thing with our naive way using its version of V, which is Q. All right, and finally we see, okay, so the ill conditioning has eventually leaked through and contaminated the answer here, all right? So really you can't get away with building the space A times A times A times A times and orthogonalizing at the end. You've got to do it on the fly, okay? So that was a great question, and that's hopefully clears that up. There was another more subtle point that I didn't so much get into. I think maybe I just mentioned it in passing. But let's mention it here. There's a difference between what's literally written on the slide for this Arnoldi process and the code that I used yesterday. And the difference is here. Okay, it's much easier to write this way. So this says we're going to take the inner products, or the dot products of A times Vj with all of the previous Vi's, which is what you want if you're going to subtract away the projections, and then we do that subtraction. Okay, so notice the order here. Compute all of those dot products and then do the subtraction. Okay, now you might say, look, there's a sum here, right? Every term of this sum is calculated one by one. Is there a chance that you don't get the full effect of these dot products when you do the subtraction? Okay, in a finite precision environment. Okay, so there are round-off errors. So let's compare. This is the classic Graham-Schmidt style as I wrote in the slides and not as the code was yesterday. Okay, in one step, compute all the dot products, and in another step, compute all the subtractions. Okay, that's a very natural way to write it, in fact. And you know, often people will actually prefer a formulation that looks like this because it maps onto routines for matrix vector products and things like that. Okay, that can be very well optimized. Okay, so this is a beautiful matrix vector product, and here's a matrix product, and so, sorry, matrix vector with the corresponding column of H. So, you know, this is a natural way to want to write it. The problem is, in the long run, you do start to lose the orthogonality of the V. Okay, so V transpose times V should be an identity matrix, right? It should have a value of 1 when you're dotting the vector with itself and a value of 0 otherwise. But over the long run, that's drifting a bit. Okay, now compare that to the version that I actually went with in the code. So here's the loop, all right? So each time, once we compute the dot product and then we do the subtraction. Okay, so the next time we're doing a dot product involving W, W has already had the previous component subtracted away. Okay, and that turns out to be a bit more numerically robust. Okay, so we're at 10 to the minus 10, now we're 10 to the minus 13. Okay, now it's, you know, it's common in code that you might even inadvertently write it one way when you weren't even thinking much about it. So if you're writing it in sort of a looping structure, you sort of naturally tend to write it this way in the first place. There is one more, this is getting a bit into the weeds now, but I can't help to mention it. There is one more trick you can add. Oops, wrong way. If you're really seeing a drift in your problem and you want to really stamp it out, you can do what's called reorthogonalization, which is just a whole second round of this same process. You've already done it once, but there's numerical drift. Round-off errors mean this is never exact. You just redo it. Okay, so you redo all the dot products, you fix up the W, and you touch up the entries in the H. And with that, you get, you know, essentially a perfectly robust approach, but for a cost, right? You're actually doing the work twice there. All right, so that's more or less the story on the mechanics of doing the Arnoldi process. Now, what you get for your money after all of this are three of our favorite relations. We got the AVM equals VM plus 1 HM bar. HM bar is the rectangular version of H. This one will play a big role in GMRes, which is coming up in the next lectures. We get this sort of long-winded version that involves splitting up the V into the VM bit and the next vector along, the VM plus 1. We'll use that today. And we have the version that tells us that the projection of the matrix onto our Krylov subspace is nothing but HM. Okay. Okay, so we did cover all of this. Okay, for us, the eigenvalue problem HM is the matrix we care about. It's the square matrix that acts like A in our Krylov subspace. And so how you end up using it is you just find its eigenvalues and eigenvectors. Okay, so this is a small scale m-dimensional problem. You can just solve that in a moment, and get a set of eigenvalues, theta, and a set of eigenvectors y of hm. Okay, so the thetas are supposed to be estimates of the true eigenvalues. Okay, so they're called Ritz values. And the y acts as the coordinate vector of the estimate of the eigenvector. So you map it back via the v, and that's called the Ritz vector. Okay, and ideally, those will be good approximations of the true eigenvalue-eigenvector pairs. But you don't want to take my word for it. You can calculate the residual. Okay, so what makes an eigenvector and an eigenvalue pair? Well, it has to satisfy this. Okay, in fact, this should be 0 if it was exact. So the difference in norm between a times u and theta times u is a measure for how converged this particular pair of Ritz value and vector is. And the point was that you can read that off your matrix at the small scale, at dimension m. So you don't need to go to the trouble of mapping them all back up to n dimensions. You can check this residual and see if it's small or not, right? And it's small or not for each of your potential Ritz vectors. Now, the thing I forgot to say, or maybe I ran out of time, I forget now, yesterday, was that there's an interpretation to this, right? This makes sense if you want to think about why these numbers together would be a measure of the accuracy of this approximation or the residual. We did talk about hm plus 1m, okay? So the lucky breakdown occurs when that is equal to 0, and generically that will occur when you've iterated the full n iterations, which is completely infeasible. In practice, if your matrix is big, the whole point is that you want to do a much smaller version of a problem and get a good accuracy of your solution. But nonetheless, if this number were 0 or very small, then your accuracy would be good for every single eigenvector. Okay, so that's getting to the point where you have essentially an invariant subspace. You've captured everything there is to know about multiplication by a in that subspace. Okay, because you tried to get a new vector in your Arnoldi process. You tried to get one. You multiplied the previous one by a. You orthogonalized against all the vectors that came before, and you were left with nothing. Okay, the norm of that remaining vector was 0, so there is nothing more to learn about multiplication by a. This is an invariant subspace. Okay, a times k equals k in that point. So all of your eigenvectors are to be found in that space at that point. Okay, so you'll get completely converged eigenvectors for every m, for every I should say, right? For each of the eigenvectors that you may pick. But the other time you'll get convergence, which is the more relevant one when you're monitoring, is that some of these final components in ym will be 0. Now, why does that tell you that you're essentially converged? Well, you map this back, you take the y and you map it back to the u via the v. Okay, so if the last component of this y is 0 or near to it, that means that the eigenvector has nothing to do with the final column of Vm. Okay, you're saying the component of the reconstruction involving that final column is 0. Well, that's perfect because an eigenvector gets multiplied by a, right? A times u equals sigma times u. So if you've got a non-negligible component in this final location of y, that means there's a non-negligible component of this eigenvector that involves the final vector of v. Okay, so when you multiply by a, you're leaking now into the next higher Krylov subspace, dimension m plus 1. So you haven't captured that full eigenvector, right, in the subspace of dimension m. Okay, so when that final component is small, you've more or less captured the eigenvector in your Krylov subspace of dimension m. Okay, so the multiplication by a keeps you in that, keeps that vector in the space. Okay, so that's the story about the residuals. Now today, we want to understand a bit more about, I always bring my MATLAB worksheets along. We want to understand which eigenvalues you're going to get for your money. Okay, we know how to monitor which have converged, but which do we expect to converge sooner rather than later? Okay, so this is just a random matrix albeit with an identity diagonal, and we're just checking everything's fine here. There's no ill conditioning of the eigenvector matrix or anything like that. This will be our test problem. And so here's the eigenvalues that we're aiming to get for this matrix. Okay, so we've got a couple of real eigenvalues here, and then a few complex conjugate pairs, another real one. Okay, fine. So just so I don't keep copying and pasting the Arnoldi code, it's just sitting in a separate function for today, but it's doing exactly the same thing that we always did, producing the v, the h, and the beta, which is just the norm of b. Okay, as long as we're here, we can check our three favorite relations continue to hold, right? AVM equals VM plus 1 HM bar, AVM equals VM HM plus HM plus 1M, VM plus 1 EM transpose. It's a mouthful, but it's an important one. And VM transpose AVM is equal to HM. So they're fine. Now let's get our eigenvalues out of this HM. That's a small problem, no trouble. And we'll compare them. So here's theta, these 8 eigenvalues from H, and here's lambda, which is 30 eigenvalues of A. But we're starting to see this first one especially looks nicely converged. The second one is sort of getting there. And you might be able to pick out sort of pairs, eigenvalue conjugate pairs that are kind of resembling what's going on down here, but maybe not quite there yet. Okay, so let's do what we need to do, which is check the residuals, and we'll just do it 2 different ways to just, again, validate our theory. So these are the full Ritz vectors, right? Multiplying back out by the v, and here's the residuals, right? So AU minus theta u, and yep, the first one is basically there, converged if you like, and the others maybe not so much. But you didn't need to do that. All of that trouble. You could have just, as we mentioned, take this HM plus 1M and the mth component of each of the y's and get the residuals that way. Okay, so that's just another confirmation that things are all working as they should. But now the question is, this is what we're going to answer today, which eigenvalues does Arnoldi prioritize getting accurate estimates for? Okay, and now surprisingly, the answer all comes down to a picture that looks something like this. Okay, the answer is, what Arnoldi is really doing is minimizing Pm of A times B in norm over all monic polynomials of degree m. Okay, now that does seem to come out of nowhere, but we're going to get there. Okay, so this picture, the contours are of the optimal polynomial, okay, of this degree m. So think of all the possible monic polynomials. So the coefficient of the highest power is 1. Many of them will do terribly at minimizing this norm, right? Pm of A times B, but one of them does the best, and that's the one that we're seeing in contour here. And so where you've got a little, a zero, if you like, of that polynomial is where the Ritz values are, okay? Because it turns out that the polynomial that optimizes this is nothing more than the characteristic polynomial of H, okay? So the matrix that the Arnoldi method generates is in fact encoding the solution to this problem, okay, in the form of its characteristic polynomial. Okay, so our Ritz values are found at the zeros of this characteristic polynomial. That's what the eigenvalues of a matrix are, after all. Whereas the eigenvalues of A are all of these red dots, and there's many more of them, there's 30 of them. And in a couple of examples, the red dot more or less aligns with one of these roots of Pm. Okay, so those are the ones that are converged or nearly so. Okay, so you can see we've got 8 roots of the characteristic polynomial, and we've got, 30 eigenvalues. And the point is, Arnoldi, in order to make this minimal, is having to essentially align the roots of the polynomial with the eigenvalues that are sort of at the extreme edge of the spectrum. Because if it didn't do that, this polynomial would be enormous way out here, right? And it would do a terrible job of minimizing this norm. Okay, so this norm would be perfectly minimized. It would be 0 if the polynomial could hit 0 for all of the eigenvalues of A. But it can't, right? It can only hit 8 zeros. But if it didn't hit this one, for instance, you can think of a polynomial if it was, not too far from, even just like over here, a polynomial grows very quickly, right? So if there's no further roots out there, no turning points or anything, it would be enormous, all right? Far outside the set of where all its roots are. So it's effectively forced to pick the roots of the polynomial to align with the extreme or the external eigenvalues so as to minimize this. Okay, now that's a lot to take in, but sort of spoil the surprise to start with. Now we're going to go through and see how this falls out, because it's quite surprising, right? It turns out that Arnoldi isn't actually solving an eigenvalue problem, it's doing this. Okay, the Arnoldi method minimizes this expression over all monic polynomials of degree m. And it does so by returning a matrix HM whose characteristic polynomial is the minimizer. Okay, so to whatever extent this method is useful at all for eigenvalues, it is a side effect of doing this. Okay, well, we need to build up a few steps. So first of all, we're talking monic polynomials. So that means this, as I said, leading coefficient here is 1. So it's going to look like this. Now we better work out what AB and A squared B and A cubed B look like. Now this is a little bit like what we started out with when we built up a Krylov subspace by literally forming these, and we said that's a bad idea. So we emphasize here this is a theoretical tool, right? At no point do we actually compute these things, but to analyze the polynomial, we'd better know what they're going to look like in terms of our matrices H, V, and so on. All right, so B is fine. It's the first column normalized. Okay, so that's beta Vm E1. A times B will be A times that. And we recognize an AVM when we see it. So we're going to expand that out using our second relation. AVM is VMHM plus HM plus 1M, VM plus 1, EM transpose E1. Okay, just multiply out the brackets and then notice we have an EM transpose EM here. Okay, so that's the dot product of the vector with a 1 in the first position with the vector of the 1 in the last position. So that's 0. So we just get the first term. Okay, what about A squared B? Well, we're going to multiply what we just had by A. And once again, we get an AVM. So we love to write that out with our Arnoldi relation. It looks like what we had a moment ago, except out here is an HM E1. Okay, so is the dot product of EM with HM E1 still 0? Yeah. Yeah, of course. Okay. We're going to check this theory as we go. Okay, so here's HM. What's HM times E1? It's just the first column. That's just another way to write the first column of HM. So it still has a 0 in the mth position. So when you dot this vector with EM that only has a 1 in that position, 0s elsewhere, you're still going to get 0. Okay, so this result remains true for A squared. Okay, so we just get an H squared. Okay, what about for A cubed? So now when we drop this expression into here, it's already got an H squared. So there's an H squared E1 sitting out here. All right, and we want to say that this dot product is still 0, but what does H squared look like? Okay, so properties of a Hessenberg matrix, you get an additional subdiagonal. Okay, so before we had 2 entries in the first column for H, now there's 3. That's okay. 3 is okay. right? That dot product still got a 0 down here. That's what really matters. So we'll be able to kill that term off and get the same result for a cubed. A cubed times b, we just get the h cubed times e1 with the vm and the beta. How far can you push this? Well, right up to the point when you've raised hm to the power m minus 2. Okay, so hm to the power m minus 2 is the highest power you can take it and still get a 0 down here. Okay, any further, that's not a 0 anymore. But at this point, yes, this dot product is still 0 because this has a 1 in the mth position only, and this has a 0 in that position, so you get this term dying off, and we have our result. Okay, the numerical values are completely unimportant. We just want to see that the two vectors are equal. But for the power m minus 1, we've lost our 0 here. Okay, so if we try the same trick for a to the m, which is the highest power we need in our polynomial of degree m, we find this last term doesn't go away anymore. Okay, hm to the m minus 1 times e1 is precisely this column. So that's a contribution now, right? These two are not equal. Okay, we can't ignore that second term anymore. So that's not the same. And that makes sense, really, if you think about it. A to the m times b, that's pushing us into the Krylov subspace of dimension m plus 1. So, of course, we surely need vm plus 1 to be able to capture that result. Okay, unless we should happen to have hm plus 1 m0 in an invariant subspace, but generically we're going to need this term. Okay, so for k less than m, we have this neat result. Right, we're going to build up a polynomial in a sec, so it's good to know what these monomial terms look like. A to the k times b has this form. And then by linearity, this is going to be the expression for any polynomial of degree up to m minus 1. Okay, any polynomial of m minus 1 degree or less of a times b, we can calculate using the corresponding polynomial of h. Hit it with the e1 on the right and the beta vm on the left, and you're good. But the result for k equals m is not as simple. Okay, we do have to carry this extra term, and that's just how it is. But there is another way that we can formulate these results. This is what we had a moment ago. If we multiply through by the vm star on the left, what are we going to get? Well, we get a vm star vm here, so that's an I. And we get a vm star vm here, so that's an I. And here we get a vm star with a vm plus 1. Okay, and vm plus 1 is orthogonal to all of the columns of v. So this term does get killed off when we do the vm star variation of this result. Okay, so now in either case, the result simplifies. This is a less than or equal to now. And so by linearity, for all polynomials of degree up to m, we can write this result. Okay, so back here, although this was not true, if we'd done the vm star, then we would have the result holding even for degree m. Okay, so this is a small vector now because we've projected it down, but they're equal. Okay, because that second term got killed off by the vm star. All right, so we've got to keep those formulas in our pocket now. And back to our polynomial. This is what the generic monic polynomial Pm looks like. And if we're operating this on B, then that's going to be in the Krylov subspace of dimension m plus 1. Okay, not m, but m plus 1, because it's got an a to the m times b in it. Okay, that's okay. Arnoldi has always done this sort of extra vector at the end for us, and it often comes in handy because we often do multiply vectors by a, so we have what we need. So because this belongs to km plus 1, the orthogonal projection of that vector is unchanged. Okay, it belongs to Vm plus 1, all right? So this is the orthogonal projector onto Vm plus 1. If you operate that onto Pm of A times B, you get Pm of A times B because it belongs to the space after all. Okay, so we'll pull out our Vm plus 1, as we love to do, and we'll group these two as a vector W, which is all of this, Vm star Pm of A times B, and a scalar, rho, Vm plus 1 transpose, if you like, Pm of A times B. Okay, so we're just shuffling things around to get something that we like the look of, because now we're going to drop in all of those formulas that we just derived on the slide before. Okay, so here's what we have. This is the thing it's going to turn out that Arnoldi wants to minimize, the norm of this Pm of A times B. So now we've got to take each of these components. All right, so here's W, Vm star Pm of A times B, okay, and rho, Vm plus 1 transpose, Pm of A times B. And the norm of this vector, given that, you know, Vm plus 1 star Vm plus 1 is I, it doesn't alter the norm. Okay, so you take the norm of this vector squared, you can forget about the Vm plus 1 and you just get the squared component norms. We're going to try to show that this thing gets minimized by the Arnoldi method. So here's the main lemma that we need. It's going to turn out that this value rho, come back. Oh, I can't go back. There we go. This value rho, in fact, is fixed. Okay, so given that this polynomial is a monic polynomial, the value of rho is determined. Okay, so it's not a degree that of control that you have, right? And you can choose any monic polynomial at all, and you get the same value of rho. Okay, and in fact, we'll give a formula for it in a moment. Okay, so for any monic polynomial Pm, this rho is fixed and given by this, right, involving quantities at the m scale. Okay, so we've got to try to derive this result. So we're going to begin with the formula on the slide here, right? Vm plus 1 star Pm of A times B. And we hope to find some of the results that we derived on the earlier slides around polynomials of A times B that we can drop into this formula. Okay, so because Pm is monic, the leading term in this polynomial is just A to the m times B, right? No coefficient there. And then here's the rest, right? Q m minus 1 of A times B, where this is just, you know, just any old polynomial of degree m minus 1. And we're going to take these two terms separately. Now, the first involves A to the m times B. And you remember from before, that was the one term that we weren't able to do anything special with beyond this. Okay, so A to the mb had this, you know, simple version of the same approach operate on the h, but it had the extra term in it. Okay, and we couldn't get rid of that, so we have to carry it here. Okay, so A to the m times b, which we do need here, has the same two terms that we just had a look at on the slide before. But we are going to hit it with a Vm plus 1 star out the front. So we get a Vm plus 1 star, drop this whole expression into here and see what falls out. And in fact, we get some good simplification of Vm plus 1 star with a Vm. Okay, well, this is orthogonal. Right? Vm plus 1 is orthogonal to all of V, so that will go away. And Vm plus 1 star, Vm plus 1, well, it has norm of 1, so this will be a 1. And so we get this expression, which, in fact, if you look up here, is already the expression that we're claiming for rho. Okay, but that's only this term. Okay, so it must be that the second term ends up to be 0. And so let's now look at the second term. The second term involves Qm minus 1 of A. Okay, and you remember that back here, right, we were able to simplify down powers of A times B for less than m to just this result. Okay, and indeed, by linearity, any polynomial of degree m minus 1 of A times B looks just like the polynomial of m minus 1 of h with the usual things front and back. Okay, so we can use that result for the second term. We split off the first term that we had to treat specially. Now the rest of the terms look exactly like this, right? Qm minus 1 of A times B. We just put the Qm minus 1 of the H front and back with the usual stuff. And then when you hit that with a Vm plus 1 star, beautifully, we see the Vm plus 1 star goes with the Vm to leave you with nothing at all. Okay, because the usual orthogonality kills that term off completely. So we have this result that this final term, this final component of our P of A times B is just fixed, right? Regardless of what monic polynomial you might have picked, you just get this value. Okay, well, let's just confirm this is true. I'm going to pick two different monic polynomials. One is just random numbers. All right, so in MATLAB, the coefficients are from highest power to lowest. So this is the coefficient of, a to the m or z to the m. And we make that a 1, and the rest can be whatever you like. Okay, so this is a monic polynomial. It's just random. And this is a special monic polynomial that comes as the characteristic polynomial of Hm. Okay, so of course the characteristic polynomial is monic, and the roots of that polynomial are the eigenvalues. So Hm is carrying around with it a special polynomial, which is this P, but they're just both monic polynomials. Okay, so now let's calculate the P of A times B for both. All right, so we use polyval M for matrix, so we're substituting a matrix in here. Polyval M of P1A times B, and then Vm plus 1 star in front of it is this number for rho. And sure enough, for the second polynomial that I just called P, it's the same number for rho. Okay, and that number is this number. Okay, it's the beta times the Hm plus 1 Em transpose Hm to the power m minus 1 times E1. Okay, so that's a big mouthful, but that's the formula that we just worked hard to derive, and we can see we got it right. Okay, so this is really just the component, or the entry in this Hm to the m minus 1 in row m, column 1. Right, so it's just picking out the bottom left, if you like, entry of Hm to the power m minus 1. If you want a fun exercise for a rainy day, you can show that this is just the product of the subdiagonal of H. So never mind the powers, right? If you go to all the trouble of calculating the powers, you may as well have just taken the product of the subdiagonal entries of H and been done with it. All of that's to say this number is not ours to change, right? By adjusting the coefficients of this polynomial, because it's monic, it does nothing at all to any of these, okay? So our job to minimize this overall expression must be focused on the W, okay? And that's ours now to try to make as small as we can, and gosh, couldn't be smaller than 0. So can we think of a polynomial that will make this term W exactly 0? Well, what was W? Well, you can, I was going to say you can trust me, but you don't have to trust me. Let's just go back where we derived it. This was it here. All right, Vm star Pm of A times B. And look at this. Didn't we get a formula for Vm star times any polynomial of degree even including m times b? Yes, we did. Right, it's beta times Pm of that Hm times E1. So we can finally use this one. Right, so this is equivalent to beta times Pm of Hm, E1, and we can make that 0. Right, there is a very good choice of polynomial that will make this exactly 0, which of course is the characteristic polynomial of H. Okay, because the Cayley-Hamilton theorem tells us that a matrix satisfies its own characteristic equation. Okay, so you put Hm into its own characteristic polynomial, you get 0. So the conclusion after all of that is that this is what the Arnoldi method truly does. It generates this polynomial Pm, and how does it represent it? By this matrix H, right? And if you want the polynomial, you should find the characteristic polynomial, but we don't actually do that. We just work with H. And this polynomial is the one that minimizes the norm of PM of A times B over all choices you could have made. Okay. And so let's just confirm that over here, although the row is the same for both of my polynomial choices, the first polynomial just has random coefficients, so it does a terrible job of making this W small. But the second choice was the characteristic polynomial of H, and it makes this W completely zero. Okay. This result says nothing about eigenvalues. Okay, evidently Arnoldi is actually solving a polynomial approximation problem. Okay, so why do we ever think it would be good at producing eigenvalue estimates, which is the actual job we're putting it to? Okay, well, here's the way to think about it. If the goal is to make this norm PM of A times B small, then a good strategy could be to make PM small at the eigenvalues of A. Okay, remember, if you're finding the polynomial of A, right, we've always said that A is going to be diagonalizable. This is the same as hitting it with the matrix of eigenvectors either side, one inverted, and the diagonal matrix of the polynomial at the eigenvalues of A, right? So the polynomial of the matrix is controlled by the values of that polynomial at the eigenvalues of A. So you win by making this polynomial as small as possible at the eigenvalues of A. Okay, but where is it actually small? Well, it's the characteristic polynomial of H. So its roots are precisely the Ritz values, okay, the eigenvalues of H. So if you're trying to make this small and you actually have control over these, then surely the strategy is to try to get the Ritz values, theta, to align with the eigenvalues lambda as best as possible. Okay. Trouble is, you don't have enough degrees of freedom, right? You only have m Ritz values, and in practice, we typically have m much less than n. So Arnoldi just doesn't have the ability to make PM of lambda I approximately zero for all of the eigenvalues, so it has to prioritize. Okay, and which ones will it prioritize well? Well, the ones at the exterior, right, or the extremities. Think of it like this. The norm of this is controlled by the norms of the matrix of eigenvectors, but that is what it is. And then all of these values PM of lambda I. If any one of these is large, that's bad. Okay, so the method can't afford to have any one of these eigenvalues too large. Okay, and if you know anything about polynomials, they explode. All right, if you take the range too far out, or the domain of the polynomial, it's going to go to infinity. Okay, so it has to make sure this polynomial is small around the exterior so that it doesn't get overly penalized by these exterior eigenvalues. Okay, and we see that happening when we go over to here. It's forced to take one of the roots of the characteristic polynomial more or less spot on to this large eigenvalue, because if it didn't, even just a little bit to the side, these contours are huge, right? This is like 60 out here. Okay, even just a little bit to the side, this polynomial would be enormous. It has to force it down to zero at this point in order that the whole thing doesn't explode. Okay, and likewise over here, it's finding that it had to put a root near to this one, near to this one. This one was okay, sort of within the scope of the others, and it was starting to converge into a few of those. And so the fun thing to do is to watch how it evolves as you increase m. Okay, so I'm going to let me move down. Okay, here we go. So my computer is running Zoom and running the code to generate this picture, but all we're doing is we're iterating over m, right? So we make m one bigger each time. It's more or less forced to hit this one straight away, right, in order to make this minimal matrix polynomial times b norm. And then it starts to find that some of these others it can deal with gradually, but this one here is the first that is converged, and you can see why, right? Even just a slight bit to the side, the norm here would be out of control. Okay, and as we iterate, we get more and more degrees of freedom, so we get more and more possible places to stick the roots of this characteristic polynomial, and more they start to align with the exterior eigenvalues. And what that does is bring the whole norm down gradually. And so when you check your eigenvalue residuals, it's these exterior ones that start to get good first. Okay. Look at this here. Like the contour is like 300 or 400, just a tiny bit to the side of this eigenvalue here. So it really is forced to have a root just right there. And that certainly explains why that one converged first. And so this is what you get with your Arnoldi method. And as it happens, as I said in the first lecture, oftentimes these are the eigenvalues that you care most about, right? So it's a sort of a natural happy coincidence that the eigenvalues the method wants to converge to are often the ones that you care about most. Okay, so as m gets bigger, this this norm keeps, well, we hope keeps improving. I guess we could play it back just once more. Okay, so by the time we got to here, a lot of these Ritz values are more or less aligned with the eigenvalues. So if you check the residuals, you'd have several more that are converged at this point. Okay, so that brings me to the conclusion of this little story. So we presented the Arnoldi method for approximating eigenvalues and eigenvectors of sparse matrices. The star of the whole show was this Krylov subspace, and it will remain so in the following lectures. We worked hard on a method to build a suitable basis for this in a numerically sort of stable way. And we derived a number of important relations. Among them was this observation that the equivalent matrix to H in our Krylov subspace land is H. Sorry, the equivalent matrix to A is H. So that's the matrix we work with in the eigenvalue problem. We calculate its eigenvalues and we map the associated eigenvectors up to n dimensions. Okay, and that gives us the Ritz vectors. Before doing so, we would check the residuals to see which ones have actually converged, and we trust those ones and not any others. But as it turns out, all the while, what the method was really doing was optimizing this polynomial problem, right? Minimizing the norm of Pm of A times B over monic polynomials of degree m, and it turns out that the optimal choice, as we showed, is precisely the characteristic polynomial of H. So if the Ritz values are accurate, then we understand that it's just because it's a side effect of this true objective, right? Which explains why it picks out the particular choices to converge to first, and the interior ones, as we saw, get left right till the end, okay? Because they're not going to hurt the polynomial approximation to get wrong in the same way as the ones at the extremities. And that is the lecture. So thank you, everybody, for your time. And we do have a little bit of time for questions. So I'll now open the chat or the microphone for questions.
Okay, so thank you very much, Tim. So questions in the chat? Not much at the moment. So maybe again, I can ask the first question to warm up the audience. So I just was wondering, so every time when someone is doing something with eigenvalues, eigenvectors, so symmetric matrices, they come as a kind of, special case, but also the most advanced one from the point of view of computation. So, and I was wondering if we apply, I know that what you were presenting today and yesterday, it was for actually general matrix, but for symmetric matrices, is there some kind of simplification or
okay, so
any other advantages?
I did wonder if I should put that in here, but as it turns out, we've had an hour of content. I may be able to fit some of it in lecture 5, but the answer to the question is absolutely. All right, so symmetric matrix, the main simplification is that the symmetry persists into the H. I mean, you can see it right in front of you. This is a similarity transform. So if A is symmetric, then so too is H. Okay, but it didn't stop being upper Hessenberg. Okay, So what is a symmetric upper Hessenberg matrix? Okay, well, if it's 0 below the first subdiagonal, it's going to have to be 0 above the first superdiagonal. So that leaves you with a tridiagonal matrix. So because it's tridiagonal, the algorithm simplifies greatly, at least on paper, because most of these dot products are 0 already out of the box, okay, guaranteed by the symmetry, so there's no need to compute them. And so it gets a fancy new name. It's called the Langshos method. And, of course, you can derive that in other ways, but you can certainly think of it as the end result of this process applied to a symmetric matrix. And there's more theory about what goes on in the symmetric case. That includes the Hermitian case, of course. But you win out there in a sense, but you lose out in a sense that the numerical drift of orthogonality can be more of a concern, okay? Because you're literally relying on the mathematics to ensure that all of these dot products are 0. But if you take a big space, you can find that by the time you get to the end and you've generated, 40, 50, however many vectors, that they're not so orthogonal to the first, second, and third in the list. Although on paper they are, in practice maybe not so much. And the extent to which that contaminates your results is interesting as well. But if you need, you can abandon the plan of relying on them being 0 and actually just do the orthogonalization as a final step, sort of like the reorthogonalization step.
Okay.
But that really does seem like it hurts, because if not for that, that's adding another whole sort of order n to the cost, order m, I should say. This is not a summation if you've only got 3 terms. So anyway, that's the story. The Langshos gets fancy new notation and everything as well. And but absolutely, yep.
So the audience, if you have questions, then just unmute yourself and ask questions. I don't want to take the whole time.
Hello, do you hear me?
Yes.
Yes.
Oh, hi. Thank you very much for the lecture. I had a question about the hypothesis. So I think initially you assumed that the matrix is diagonalizable.
Yes.
So if it's not the case, like, does the algorithm completely mess up, or do we just have the issue that we struggle with estimating the multiplicity of the eigenvalues?
Yeah. So I'd like to present the case where it's diagonalized because it makes the theory straightforward. Sometimes you can recover the results using, Schur decompositions and other things like that. But there's also the issue that you always need to be careful, and this point's been made well in many different places. Jafethan, for one, always makes sure to bring this up. If the eigenvectors are not well conditioned, then it might be that you're asking the wrong question of the problem, right? So if you're dealing with a matrix whose conditioning of eigenvectors is very poor, then you may be able to calculate somewhat accurate estimates of those eigenvalues all the same, but the conclusions that you draw from those may not be so meaningful, just because the norm of that, somewhere I've got a norm of an x and a condition number just to make the point. These norms of these x's float around, all right? So if this condition number is huge, then the consequences can be that the results aren't applicable anymore. Okay, so, and of course the limit of that is that the thing is actually singular. Okay, so the advice always given is go away and think about whether your problem really is suitable to be analyzed using eigenvalues, or whether it's something else, pseudospectra or whatever else, that makes more sense in that case.
So I think these methods are used to, like for example, we do finite element method, and we want to solve for matrix vector system. And so do you think that it happens often that the matrix is non-diagonalizable, or it's pretty rare actually in this case? I have no idea.
Well, generically it wouldn't happen, but of course, if your problem has specific structure that that leaks into the matrix and sort of forces it to be so, then that's just how it is. But if you just pick random entries in a matrix, not that real problems are made of random entries, but that's what we've been doing here, then you won't run into that situation.
Okay, thank you.
Okay, but every problem is its own problem. So you can always analyze the problem beforehand and see what you're going to be dealing with, and then decide whether this is going to be a suitable method.
Okay, so more questions. So the chat is empty. Well, if no more questions, then I guess we can finish for today. So thank you very much, team, and thank you very much, everyone. So tomorrow it's Chen who is presenting, right?
Yep.
Okay, and you will come back on Friday.
Yes, so we'll do another 2 weeks, 2 hours of linear system problems now, GMRes, and then I'll do what I can on Friday to sort of tie the things together and talk about extensions and other ideas and things like that.
Okay, all right. So thank you very much, everyone, and see you tomorrow.
Okay.
Thanks. Bye.